All right, so on this section, we're talking about something called confidence intervals. And confidence intervals are something very important for us in statistics. For us here, it's called a confidence interval for proportions. Remember, there's the difference between proportions and means. And the reason why we have this lovely fishing dude here is because we're going to be talking about nets, or we're going to be talking about capturing. Because when we create a confidence interval for proportions, we are interested in capturing the true p-value, or the true proportion value. So just a reminder here, the difference between proportions. Anytime you hear percentages or fractions, thinking proportions, means would be quantitative data that's measurable on a ruler or a scale. Proportions would be the proportion of brown-haired girls or the proportion of orange M&Ms. The true proportion is p. The true standard deviation is sigma. And then when we talk about statistics, remember that's when you take a sample. And the sample of, so everyone who took a cup of M&Ms and we counted the proportion of orange M&Ms, we'd call those p hats. And then we have a standard deviation, which is the standard deviation of p hat. So a nice way that I like to remember it is that you have p for population, or the true. So the parameter and the population, those are the p's and the sigmas, but the statistics are the things you've actually measured, and those are in your samples, the p hats and the standard deviation of p hats. Before, we looked at standard deviations for things. So for how do you find the standard deviation of p, or for p hat, and we said that you can say that standard deviation is pq over n with a square root, and we also looked at y bar being sigma over square root of n. Notice though that it's asking for p and q, which are population parameters, known values there. If we don't know these, because we're trying to guess at the population, because let's say I don't know what the true proportion of orange M&Ms in a bag is, I haven't asked the M&M company, I can't plug in P and Q. I might, however, know P hat and Q hat, meaning I know what I found in my sample, and so I think that that's roughly close, or at least I'm hoping it is. So when I can use P hat and Q hat instead of P and Q, this is something we call standard error. So if you don't know the parameter or the true value for anything, whether that's P or sigma or whatever, you can use sample statistics to estimate the parameters. However, when we do this, anytime that you estimate the parameters, so when you estimate the standard deviation because you don't know the true values to plug into these formulas here, those estimations are called standard error. Error does not mean anything bad happened. Here, error means variability. Okay, so do not think that error is, oh, we made a mistake in our calculations. Instead, I want you to think error is wiggle room. How much variation should I expect to see in my samples? So it's the same formulas, but the slight difference is that we use p hat and q hat and s instead of the p, q, and the sigma. So when we talk about a confidence interval, remember how we're going to use these pieces here. And I'm going to switch over really quick to remind us about sampling distributions. So what we're saying now is that we could talk about this curve. We're hoping to land at P, because we're hoping to figure out what is the true P, and this standard deviation that we talked about. Now what we're going to have is we're going to have instead our sample. So we have P hat, and we're going to try to estimate that standard deviation with standard error. So we'll have P and Q hats over N as standard error of P hat versus the true P, the true Q over N as the standard deviation of P hat, because that's when we actually know our P value here. So a confidence interval is this idea of how do we capture. It's a sampling distribution model of P hat centered at P, because again, that's what we think the center should be with a standard deviation. But since again, we're going to use standard error to help us estimate that. And then we know about our 68, 95, 99.7 rule. We know that 68% of all samples will have p hats within one standard error of p, or one standard deviation, same idea. 95 is the 2 standard errors, 99.7 is the 3 standard errors. So from p's point of view, p hat's point of view, from p hat's point of view, this is your sample that you took. We're hoping that the true p that we're trying to elusively find falls near p hat. Now, it'd be really nice if he fell right here, right on p hat, right? That would be a perfect world. But we know he might be a little off. So he might be all the way out here. He might be maybe not quite on par, but close. And we know that hopefully he should be fairly close. It would be weird if he was far off. And again, maybe you can kind of see where this is going. We're going to use this idea of standard deviations or standard errors to tell us how likely it is that we have captured the true value p. Now here's the thing about the true value p. We never know it. We never see it. We're just hoping. We're hoping that it falls somewhere in here. So we create these nets, if you will, and we say, well, it would make sense that within 2 standard deviations, since that's 95% chance of being around here, we think there's a 95% chance that it falls close. That's what this is saying. This is saying there's a 95% probability that p hat is no more than 2 standard deviations away from p, the true value. So if you were to think about this being the true value right here, the true p, our p hat should not be that far off. So what we're saying is, okay, if p hat should not be that far off, then p should not be that far off either. Again, let's go back to a picture down here. So if we were to do the true p value, so this red is true population. Here's true p, and here's his standard deviations. It is possible that our sample, let's say, falls a little high. So our actual sample was a little higher than you would find the actual p at. So this is the p hat, or the sample. And so when we look at his standard deviations, how far off is true p from p hat? Well, they're within a standard deviation of each other. And that should make sense. That shouldn't feel too weird. Maybe, and another way to say this is that p hat might fall a little higher than p. Maybe p hat fell up at 2 standard deviations. Again, that could be okay. We could expect that it would fall within there. It's going to be really weird, though, if p hat fell, say, over here. That would seem a little far up. It's possible, but not as likely. Since we don't know the true p, the red, we're trying to estimate that red, we're trying to estimate that true p by only doing, why does it keep doing that? There we go. By only doing our p hat. So by getting the sample, we're trying to say, okay, I could be 95% confident, because that would be 2 standard deviations, 95% confident of capturing the true p. If it happens to fall out here, that's the weird 5% chance. That's what we mean by a confidence interval. So we're talking about chances of capturing the true p. When we do this, we're talking 95 is a nice one because it's 2 standard deviations. Here's another picture that kind of shows what we're talking about here. Whoops, sorry. Think of if you took lots and lots of samples. So each one of these blue lines represent someone in our class taking a sample, and the red dots are the p hats that each of you took in your sample. Now here is the true proportion, the green line. Many people's samples, if we put 2 standard deviations, which are the blue bars, on either side of the p hats that everyone took, most of those 2 standard deviation lines are going to somehow capture the true p, the green line. There are a couple in here, like this first one, and this one right here, and this last one down here, that don't, but most of them at least fall somewhere within 2 standard deviations. This is a great picture that you want to think about when we're talking about what does a 95% confidence interval mean. It means out of all the samples we could possibly take, and again, these are only 20 samples, but out of all possible samples, 95% of all possible samples should fall within 2 standard deviations of the true p-value. So here we go. 95% of all 95% confidence intervals to contain the true parameter. Now, not any one interval, but all of them together. So this is important. If we just focus in on just this one interval, what's the probability that we captured the true p? Well, either we did, in the case of the second one, or we didn't. It's a yes or a no. So for any single one, we don't know what your chances are for any single one because it's either yes or no, you did or didn't. But if you were to look at all of them together, 95% of all of them should capture the true p. So this is another important thing for us here. We can claim with 95% confidence that the interval of p hat, whatever our sample proportion is, plus or minus 2 standard errors away from p hat, contains the true population proportion p. Margin of error is what we call this 2 standard errors thing here. Now, we're doing 95%, so margin of error here is connected to this piece. Sometimes we'll do 90% instead of 95, or sometimes we'll do 98%. So this can change. We'll talk about that in a second, but this back part is the margin of error, and this is the estimate. So again, think of it as estimate plus margin of error. That's a confidence interval. If you want to be more confident of capturing the true p, then it should make sense for us that the net needs to actually be wider. So for example, here's a wider net. It goes out 1, 2, 3 standard deviations. So p hat plus 3 standard errors. That would give us 99.7% confidence because it's a bigger net. So when you're more confident, it makes your net bigger, which means you're less precise. So it's always a balance between certainty and precision for this. All right. Again, we could use different types of confidence levels, 90, 95, and 99. Whether you have 90, 95, or 99 is going to depend on how far out you go based on your normal model again. So if you think about back to our normal model idea here, think about our confidence intervals. Again, we're trying to capture the true p. How wide do we want to make our net? If we make a net that's only this wide, it's a pretty tight interval. We could say, hey, I think we're going to be between only this value and this value, but it's pretty small. It's not a very wide chance. If we make our net a little bigger, now we have a greater chance. We can say, oh, between this value and this value, and I'm actually pretty confident. That's a pretty big size net. So we're always going to try to balance what do we mean by this. One example would be snowfall. Think about all the snow we've been getting. The weatherman could say, tomorrow I think we could have snow between 1 and 10 inches. Well, between 1 and 10 inches is not actually very telling because that's a really wide range. But could he be confident that it was between 1 and 10 inches? Well, sure, he's bound to be right. But if he makes it smaller and he says, I think we're only going to get between 5 inches and 6 inches, that might be more helpful for you and me. That lets us know, oh, okay, so it's a decent amount of snow, but hopefully I'm not going to break my back shoveling it. But it's harder for him to be exactly right. There's a smaller chance, a smaller percentage that he actually falls between 5 and 6. Whereas if he tells us between 1 and 10, he can have a good reputation as the weatherman who is always right. But for you and I, trying to figure out how much time we need to get up early in the morning, this one is less helpful because it's less precise, even though he is more confident. So less confidence means greater precision. Less precision means greater confidence. We're going to pause it there.